English for engineering.
Tiếng Anh ngành kỹ thuật.
10.1.
Obviously, a tubular steel tower only gives you sufficient structural strength if you give it adequate protection from corrosion, the big problem with offshore installations. So technically, you could say steel is inappropriate in that environment.
They make ships out of it.
I know, Loretta, but only because there's no cost-effective alternative. But we're not talking about ships. We're talking about fixed structures. The point is, I think we should look more seriously at alternatives to all steel supports. And the obvious alternative is reinforced concrete.
We've already looked into it, though, and it wasn't cost-effective.
Not in the short term, but we didn't really look into it properly over the long term.
But you made the point yourself, Mike, that steel is completely ineffective if it's corroded. And one of the main constituents of reinforced concrete is steel.
It's protected, though, isn't it? It's embedded inside concrete. That's a much more effective protection than paint.
Not necessarily. If we're talking about the long term, as you say, what happens to concrete when it's exposed to the sea for a few years? It erodes, which means the steel eventually gets exposed. You look at concrete coastal defenses. How often do you see the concrete all crumbling away and all the steel exposed?
That's due to inconsistent quality, though. You only get that problem if there's insufficient cover. As long as there's appropriate cover at design level and the construction quality is consistent, then there shouldn't be a problem.
Isn't inadequate cover more of a problem in a slender structure, though? You'd probably have less cover compared with the big lumps of concrete they use for coastal defences.
Not if...
Just a second.
Yes, Hanif?
Let's just think about what we're trying to resolve here. The key issue is, what's the most suitable long-term solution? And in both cases, we're saying steel is necessary, either in an all-steel tubular structure or in the form of reinforcement inside concrete. But obviously exposed steel is unsuitable because of the problem of corrosion. So the question is, what's the most reliable way of protecting steel over the long term? And we have to bear in mind that just because something requires regular maintenance, such as painting, that doesn't necessarily mean it's unreliable. As long as the maintenance is consistent, the key question is, what's the most economical approach? So, painting a steel structure every couple of years is uneconomical only if the cost of painting is more expensive than the additional cost of using concrete at the time of construction.
So, to determine the most efficient solution, we need to assess the lifespan of a reinforced concrete structure. If we know that, we can determine how many times the equivalent steel structure would need to be repainted over that same period, and what the cost of that would be.
Yeah.
But this is really the point I'm making, Hanif. We can't categorically say that reinforced concrete is inefficient unless we look into it in detail.
Of course not. Look, let me make a suggestion. I was thinking...
10.2.
With very tall structures, one of the main loads you need to take into consideration clearly is the mass of the structure, its weight. Due to gravity, that mass exerts a downward load which has to be transmitted to the ground. So that downward force means the structure is in compression, especially near the bottom. Obviously, the closer you are to the bottom, the more compressive force the structure is subjected to. But with tall structures, downward load compressing the structural elements is only part of the problem. Another major force acting on the structure is wind load, which is a horizontal load exerted by air pressure against one side of the structure. Because the structure is fixed at ground level and free at the top, that generates bending forces. And when elements bend, you have opposing forces, compression at one side, tension at the other. And at ground level, the wind effectively tries to slide the structure along the ground, and the foundations below the ground resist that. The result of that is shear force between the substructure and the superstructure. The wind generates tensile loads on the foundations of tall structures as well, as the bending action tries to pull them out of the ground on one side. A bit like a tree being uprooted by the wind. So the foundations need to rely on friction with the ground to resist the pull-out force, just as tree roots do. The action of the wind can also generate torsion. You get a twisting force sometimes when the air pressure is comparatively higher against one corner of a building. Although that's less of a problem with chimneys because of their circular profile. With very large masses of concrete, you also have to think about the forces generated by thermal movement. When concrete absorbs heat from the sun, you get expansion. As soon as the sun goes in, there's contraction. That movement can be significant over a large area, especially as the sun generally heats one side of a structure much more than the other. So there are all kinds of different forces acting on a tall structure.
10.3.
The record speed exceeded the standard operating speed by a huge margin. It was 80% faster at its peak. So you would imagine that the TGV used for the record run was heavily modified. In fact, that wasn't really the case. The train was modified to a certain extent, but with a few exceptions, it was essentially just an ordinary TGV. As you can see from this slide, one of the biggest differences was that the modified train was significantly shorter in order to make it lighter. There was a 50% reduction in length down to 100 meters, compared with the 200-meter standard length. The coaches being pulled were perfectly standard. The only differences were that some of the seats had been removed to make way for all of the monitoring equipment that was carried on board. And some changes were made to the bodywork to make it slightly more aerodynamic, which meant the drag coefficient was reduced by 15%. The wheels on the modified train were marginally bigger than the standard size. The diameter was increased by 19% in order to reduce the speed of revolution, to limit friction and centrifugal force. And the power of the electric motors was substantially higher than the standard units, boosted by 68%. But none of the changes was fundamental. So my point is, standard high-speed trains can be made to go faster by a considerable amount.
10.4.
In the late 1940s and early 50s, the United States Air Force carried out a series of experiments to explore how much physical stress the human body could withstand. A key aim was to test how much G-force pilots were able to cope with and see what would happen if they exceeded their limits. Led by Air Force Dr. John Paul Stapp, a number of spectacular tests were carried out at Edwards Air Force Base in California, a location suitable for the experiments thanks to its 600-meter rail track, specially designed for high-speed rocket tests. A rocket sled capable of reaching speeds approaching the sound barrier was mounted on the track. On top of the sled, named Sonic Wind, researchers fixed a seat intended for an abnormally brave volunteer. Refusing to give the dangerous job to a member of his team, the man in the hot seat was John Stapp himself. Over several runs, Stapp was subjected to progressively greater extremes of force. Each time, he resisted. Eventually, the time came to take the ultimate risk, to surpass what many doctors believed to be a deadly level of G-force. And so, on December 10th, 1954, Stapp was strapped onto Sonic Wind for the mother of all rides.
10.5.
That day, Stapp was subjected to extremes of force beyond the imagination. When the sled's rockets fired, he shot from 0 to over 1,000 kilometers per hour in just 3 seconds, subjecting him to 20 Gs. When the sled hit the pool of water in the braking zone, it was like hitting a brick wall. Stapp slowed from the speed of a bullet to a complete stop in little more than a single second. Incredibly, John Stapp survived the ride, although so much blood had rushed into his eyes that he was unable to see for some time afterwards. Before the test, doctors had believed that human beings were incapable of surviving forces greater than 17 Gs. When the sled hit the water, Stapp had pulled a crushing 46 Gs.
10.6.
I think what he's suggesting in terms of acceleration and deceleration forces is reasonable.
Yeah. 2G sounds about right. Anything less than that and the track length's going to exceed the size of the site. And if you start getting close to 3G or beyond that, then that's probably going to be a bit too much for the average passenger.
I'd say so. His calculations for the total distance for acceleration and deceleration seem about right. The problem I have is with the length of the track. I think his 10-kilometre figure is okay for an ideal world scenario, but it doesn't leave much margin for error.
No, because at full speed you're going to be covering, what, a kilometre every 3 seconds? So if there's some kind of problem, you're going to be eating up the kilometres at a pretty frightening rate.
You can say that again. I think he'll need every kilometre of track length he can get on that site, plus some sort of emergency stopping facility at the end of the line, just in case.
Definitely, yeah.
Then I don't know what you think about using wheels instead of skids.
Well, technically, it's feasible to build wheels capable of spinning at that sort of speed, because it's been done on land speed record cars. The only problem is, if you get a wheel failure at the kind of speeds we're talking about, the consequences are going to be unthinkable.
Yeah. I haven't calculated exactly what centrifugal forces they'd have to cope with, but for wheels of about 500 mil diameter at full speed, I worked out they'd be spinning at over 13,000 RPM.
Yeah, that's a lot. Plus, of course, skids should give better frictional resistance under braking.
Possibly.
Maybe not?
Well, the friction from wheel bearings spinning at that sort of speed might be higher. And the skids wouldn't be in permanent contact with the rails, don't forget. But anyway, I think skids are the only safe option.
I'd go for skids, definitely.
And then for the brakes. I think the first point is that for the initial deceleration, even without applying any brakes, the aerodynamic resistance is going to be huge. In fact, that alone might even exceed 2G for a short time.
Possibly. It'd depend how much drag there was. Which obviously depends on the bodywork design, doesn't it?
Yeah.
I don't like the idea of a friction system against the rails. It would have to withstand a tremendous amount of heat.
Yeah, I think that's a non-starter at these kinds of speeds. Aerodynamic braking has got to be the best option. Possibly you could deploy flaps initially at top speed, then maybe release a parachute as a second stage. Yeah, maybe deploy the parachute at, I don't know. What sort of speeds do dragsters reach? They use parachutes, don't they? What do? 400 Ks?
A bit more, I think. 450, something like that. There's also the option of reverse engine thrust, like they use on aircraft.
In that case, though, you'd still need another system, in case you get an engine failure. But it's a possibility. I think the bottom line is that it needs a combination of systems to make it absolutely fail-safe.
Ngoại ngữ chuyên ngành.com